Okay, so now what we're going to do is look at a bit more of the chemistry of alcohols, and we're moving into the realm of alcohols being converted into ethers. Ethers are compounds in whose molecules two organic groups are joined to the same oxygen atom. As an example, ethoxyethane, also known as diethyl ether, which is an example of what's called a symmetrical ether. The two groups are identical. Methoxyethane, ethyl methyl ether, is an asymmetrical ether, simple aliphatic ether. You can have two ether functionalities as long as they are at least 2 carbons apart. If they are 1 carbon apart, the functional group is referred to as something else, and the chemistry differs slightly. But if the ethers are far apart from one another, like they are in 1,2-dimethoxyethane, which is actually a fairly well-used solvent, then the chemistry remains ether-like. You can have ether functionalities in a chain with other functionalities, and here is a chloroalkane. So chloroalkanes can be used to substitute to other systems to introduce an ether-bearing chain into synthesis, for instance. And note the IUPAC nomenclature of that system. The ether linkage can be within ring systems, and these are examples of heterocyclic ring compounds. A heterocycle is a ring system with a non-carbon atom in. So if you look at the extreme right-hand side structure, which is a cyclohexane analogue, this will be regarded as a heterocycle. The systems are called oxyran, or ethylene oxide, oxytan, which is a 4-membered ring ether, oxalane, a 5-membered ring ether, and oxane. As with the alkanes, the 3-member ring and the 4-member ring systems are quite reactive. The 5 and 6 can be encouraged to open, but need some extreme, not extreme chemistry, but different chemistry to do that. But the 3 and the 4-member rings really don't like being strained and are quite reactive. And in fact, epoxides, which is the another name for the oxyran type structure, and epoxide, are when you see that functionality, you should regard it as a potential alkylator of DNA. It's that reactive. And there's a link to look at the ether group chemistry. Okay, a little play on words here, origin of symmetry. People that are Muse fans will notice the symbol in the right hand corner. Just occurred to me when I was putting the slide together to pop that in, as I'm a Muse fan. Symmetrical ethers may be prepared by dehydration reactions. Primary alcohols are the most useful starting materials, and this is the type of chemistry that can be formed. And we can see that we've got sulfuric acid here. Now we've met sulfuric acid before with alcohols leading to dehydration reactions to give alkenes, but the chemistry can be manipulated such that elimination of water can occur across 2 molecules and introduce an ether linkage. Obviously, elimination reactions are a competing reaction and must be taken into account, but you can use this chemistry productively to synthesize ethers. They're thought to proceed rapidly via a sulfuric acid ester or a sulfate, following this type of mechanism. An asymmetrical ether synthesis can be utilized. The Williamson's ether synthesis is a way to make asymmetrical ethers. You can also use it to make symmetrical ethers, but the previous slide would only result in symmetrical ethers. If you used mixed alcohols in the previous slide's chemistry, you would get a range of products from that chemistry. This helps control the reaction. So you would have an alkoxide ion, which is an O- bearing species derived from an alcohol, and that O- is nucleophilic and would attack an appropriate carbon on an alkyl halide to give an ether and displacement of that halide or an appropriate leaving group. It doesn't have to be an alkyl halide. We'll look at that later on another course. Here's an example. So we've got the isopropoxide ion, which would be derived from isopropanol, attacking benzyl chloride. And notice the naming of that compound, benzyl, which is the blue fragment of that group. Benzyl chloride, we're introducing the isopropoxide portion into that molecule, and we've ended up with an asymmetrical ether and displacement of chloride ion. Alkoxides are readily made from alcohols. If you take an alcoholic liquid like isopropanol, ethanol, and so on, you can just drop sodium into it, like sodium would be dropped into water and would react vigorously with water. Sodium will react vigorously enough with most alcohols, particularly the liquids, to give hydrogen and sodium, the sodium salt of the alcohol or an alkoxide, and this can be used in the above synthesis. And there's a link to the Williamson's ether synthesis. So a student would be expected to be able to recognize the ether functional group and name simple compounds, construct a structural diagram from a simple name, remember how to extrapolate physical chemical properties yet again of the ethers from principles learnt from alcohols and previous systems, suggest synthetic schemes with plausible alternatives for designated ethers. If you look back at that ether example, isopropoxide reacting with benzyl chloride, you could envisage reversing the reaction and having benzyl alcohol attacking maybe the isopropyl chloride, and you must be aware that is a possibility, that you can reverse the chemistries for those fragments. Find examples of those. Recognize the fact that oxygen can be part of a cyclic system, and they can be very stable, and in fact drug substances use cyclic systems with oxygens in to increase water solubility of a cycloalkyl fragment. Okay, a good student should be able to extrapolate the chemistry readily from what we've learnt to those of sulfur analogues, thioethers for instance, due to the recognition that their chemistry is extremely close to that of oxygen. Thiols are in fact slightly more acidic than alcohols. So take oxygen examples and substitute sulfur to learn these things. This can go right back through all of the alcohol chemistry. Everything you've learnt for the OH group applies to the SH group. There are some variations with sulfur chemistry that we'll learn when we look at sulfur chemistry in particular later on, but you should be able to rewrite in effect everything you've learned with the oxygen system for a sulfur system. So alkyl thiols, aromatic thiols, so the sulfur analogue of phenol, all through the previous slides. And so be aware of that, and this is because sulfur is in the same periodic group as oxygen.